Hi and welcome. So now we're going to start talking about doing compositions of inverse trig functions. And here we're going to focus on using the special angles, and I'll do another video using the other angles. So if it's been a while since you've seen function composition, let's do a quick review. So we usually see something like f of g of x, and the way this works is that we start on the inside and work to the outside. So this set of functions, this composition of functions, takes in an input x, it goes into the function g, and it outputs g of x, whatever that is. So g gets applied to x and we get this output. Then this output becomes our new input for the function f. So we input g of x into f, and then we get an output. So that output is f applied to the g of x. So we start with that input x, and it goes through both functions, and we get our output. So this is going to look similar once we start looking at our trig functions. So the way we're going to see it most often is something like cosine of arcsine of a. So I'm choosing cosine and arcsine here. You could choose other things, of course. I'm just giving an example. And we'll start with the inside and work our way out in a similar way. So we give a to a function, so we start with that input a, we give it to the function arcsine, and so it outputs arcsine of a. Then that becomes our input to cosine, and we get an output of cosine of arcsine of a. And the way this works is that we're starting with a value a, and it's telling us the angle first. So I give arcsine a value, it tells me the angle that it came from, and then I'm going to give that angle to cosine, which will then tell me the value that goes with it. And by value, I just mean something that isn't an angle, really. So some sort of scalar, some sort of number, that sort of thing. So we're sort of starting with a value, and we're getting an angle in the middle, but then just getting a value back out at the end. So this is good to remember when you're doing these problems, that if it's inputting a value, you should be getting a value back out, at least when there's this composition happening in this particular way. Alright, so let's try some examples so you can see what this looks like. For our first example, let's simplify and evaluate tangent of arcsine of square root of 2 over 2. So I'm just going to put some colors on these so I can help keep them apart, and we're going to start on the inside. So we're going to start with arcsine of square root of 2 over 2. This asks, what angle has a sine value of square root of 2 over 2? And specifically, it's asking which angle in quadrants 1 and 4, since arcsine is defined in those quadrants. So we have a little mini problem to do with the inverse trig that we have to do first, and then we'll use tangent afterward. So we're sort of combining the things we've learned. We're doing some inverse trig, and then we're doing a trig problem with the tangent at the end. So I first ask myself, is our input positive or negative? Well, square root of 2 over 2 is positive, so this is quadrant 1 for my arcsine. Then I'm going to use a reference triangle, but you could also look at a unit circle. Sine is opposite over hypotenuse, so my sides on my triangle will be labeled square root of 2 and 2, and I know that this corresponds to the reference triangle for 45 degrees, or pi over 4. You can also look at a unit circle, and you should see that pi over 4 has a sine, or a y value, of square root of 2 over 2. So I've solved this first part. I can now say that arcsine of square root of 2 over 2 is equal to pi over 4. Now we're going to move to the outside. So I now have tangent of this thing I just found. So I can write this as tangent of pi over 4. I'm replacing the arcsine of square root of 2 over 2 with what I've now found it to be, which is pi over 4. So now tangent of pi over 4 is just like an older problem that we've seen before, and so we're just going to solve this. Part of why I like drawing the triangle is that you can use this same triangle now if you'd like, or you can also use the unit circle too and do y over x, that's also fine. But on this reference triangle, I know that the adjacent side is going to also be square root of 2, just because this is one of my really common reference triangles, the 45, 45, 90 triangle. And so tangent is opposite over adjacent, which is square root of 2 over square root of 2, which is just 1. And so I know that tangent of pi over 4 is 1, and I can write my final conclusion. Therefore, I can say tangent of arcsine of square root of 2 over 2 is equal to 1. And that's my final answer. So here we started with an input of square root of 2 over 2, that's a value, and we ended with an output that was also a value, so it was 1. We had an angle in the middle, that was the pi over 4, but we ultimately ended up with a value again at the end. Let's try this on another example. So let's simplify and evaluate cosine of arctangent of negative square root of 3. Why don't you pause the video now and see how far you can get. Remember, we start on the inside, and you want to look at that input and determine if it's positive or negative to help you find the quadrant. So why don't you pause and try it now, and then come back and we'll do it together. Alright, so starting with the inside, I have arctangent of negative square root of 3. This asks, what angle has a tangent value of negative square root of 3? And specifically, I want to know which angle in the interval from negative pi over 2 to pi over 2, which is quadrants 1 and 4. So that input is a negative square root of 3, which means that we're in quadrant 4, since that's where tangent is negative. It's positive in quadrant 1, but it's negative in quadrant 4. Then I'm going to draw myself a triangle positioned in quadrant 4, and I remember that tangent is opposite over adjacent. So negative square root of 3 is going to be that opposite side. I know that it's negative since the y value is negative here. And then the adjacent is just 1. And part of how I feel confident doing this is that I know it's one of my reference triangles. So this negative square root of 3 corresponds to a reference triangle, and so this should start to look familiar in a moment. So specifically, where I have negative square root of 3 as the opposite, this is the pi over 3 reference triangle, which you can really think of as negative pi over 3 here, since we're in quadrant 4. Then I'm just going to label the hypotenuse because I know I'm probably going to need that, and the hypotenuse is 2. Again, I know all of these things because we've already learned these reference triangles, so having them near you as you're doing this is really going to be helpful. And I can now make my conclusion about the inside. So the arctangent of negative square root of 3 is negative pi over 3. So I take that negative angle to be in quadrant 4, and that's why it's negative pi over 3. Now we can move to the outside. So I want cosine of this value. So I found that arctangent of negative square root of 3 is negative pi over 3. So I'm looking at cosine of negative pi over 3. Now this is hopefully a problem we're comfortable with. We could use this same triangle that we already drew, or you could even use the unit circle if you'd like. So on our triangle, cosine is adjacent over hypotenuse, and so that's 1 over 2. And there we go. This is my final answer. I can say, therefore, cosine of arctangent of negative square root of 3 is equal to 1/2. We started with a value, negative square root of 3. We got an angle in the middle, negative pi over 3, but we ended up with a value again at the end, which is 1/2. Okay, so this process that we did in these last two examples, we're going to repeat this same process once we start to use other angles, and so that's why I've been trying to emphasize the triangles here. So in the next video, we'll do more of these, except there will just be other angles instead of the ones that are on the unit circle, but we'll get more practice with the same process. That's it for this one. Thanks so much for watching, and I will talk to you in the next one.